Hello everyone, in this video we will discuss about signed multiplication using Booth's algorithm. We now discuss multiplication of 2's complement signed operands generating a double length product. The general strategy is still to accumulate partial products by adding versions of the multiplicand as selected by the multiplier bits. For a negative multiplier, a straightforward solution is to form the 2's complement of both the multiplier and the multiplicand and proceed as in the case of a positive multiplier. So here we will be discussing about signed multiplication, means multiplication for the signed number. So whenever we get a negative multiplier, we have to convert that into a means we have to take a 2's complement form of the multiplier. This is possible because complementation of both operands does not change the value or the sign of the product. A technique that works equally well for both negative and positive multiplier, that is known as Booth's algorithm. Booth multiplication algorithm is a multiplication algorithm which is used for two signed binary numbers in 2's complement notation. The algorithm was invented by the scientist Andrew Donald Booth in the year 1950s. Andrew Donald Booth was a British electrical engineer, physicist, and computer scientist who was an early developer of the magnetic drum memory for computer. He is known for his algorithm, that is Booth's multiplication algorithm. The Booth algorithm is it is mainly used for multiplication. It is a multiplication algorithm that allows us to multiply two signed binary integers in 2's complement respectively. Means we will be considering both positive and negative integers. It is also used to speed up the performance of the multiplication process. Booth algorithm, we'll see the basic steps required for Booth algorithm. In the step 1, if the multiplicand or multiplier m or q is negative, then find the 2's complement of respective negative number. Step 2, find the recoded multiplier q dash by referring Booth recoding table. So for this algorithm we need to refer a table which is called Booth recoding table. So here we will be modifying the multiplier and we call that as a recoded multiplier q dash. Then in the step 3, multiply with 2n bit extended for each partial product pi, where minus 1 means 2's complement of multiplicand m. Then finally we need to find the final product of product P with a 2n number of bits. So this is a Booth algorithm recoding table. So here you can see we have a bit I minus 1 and bit I. So we need to consider these bit position. So and here in the second column we can see the version of multiplicand selected by the bit value in the multiplier. So if it is the bit value in the multiplier, it is 0 to 0, then we need to take 0 into m. The version of multiplicand will be zeros. In the next stage, that is if the bit I minus 1 is 1 and bit I is 0, means it is moving from 1 to 0. The bit value is 1 to 0. Then we need to consider the multiplicand as it is. The version of multiplicand will be plus 1 into m, that is nothing but the multiplicand itself. Then in the next, if the bit value is 0 to 1, then we need to consider the version of multiplicand as minus 1 into m. So minus 1 into m means you need to take 2's complement of the multiplicand value. Then next, the bit value 1 to 1 means we need to consider 0 into m. Means all the partial product values will be 0 with respect to the multiplicand bit value. So this is a Booth recoding table. So these values will be considered for the multiplier recoding. So what we get after this is nothing but recoded multiplier. So in general, in the Booth scheme, -1 times the shifted multiplicand is selected when moving from 0 to 1, and +1 times the shifted multiplicand is selected when moving from 1 to 0, as the multiplier is scanned from right to left. So -1 times means we need to take 2's complement of the multiplicand value. +1 times means we need to consider the same value. So whatever the multiplicand value, we need to consider the same. So now we'll see one example. So this is the original multiplier value. We are just considering an example how to recode the multiplier. So here, according to the Booth's recoding table, the bit value will be considering from bit I minus 1. Means we need to consider the previous bit value. Okay, so for that we'll assume here a 0. Okay, we'll imply 0 here as a previous value, I value, that is 0. So 0 to 0, we need to refer the Booth's recoding table. 0 to 0 means we'll get 0. Then 0 to 0 again 0. Then 0 to 1 means you will get -1. 1 to 1 means 0. Then 1 to 0 plus 1, 0 to 1 minus 1, 1 to 0 plus 1, 0 to 1 minus 1, 1 to 1 0, 1 to 1 0, 1 to 0 plus 1, 0 to 0 0, 0 to 1 minus 1, 1 to 1 again 0, 1 to 0 means plus 1. So like this we need to recode the multiplier. So this is nothing but recoded multiplier, that is Q dash. Now we'll consider one small example here. Recode the multiplier 1011 for Booth's multiplication. So here what you have to do is 101100, and you have to add one extra 0 here to refer this as a previous bit value, bit I minus 1. So we'll imply or we'll add one extra 0 here. So now according to the Booth's recoding table, we'll recode this multiplier. 0 to 0 means 0, 0 to 0 0, 0 to 1 means -1, 1 to 1 0, 1 to 0 means +1, 0 to 1 means -1. So this becomes Q dash, that is nothing but recoded multiplier. So considering 2's complement signed operands, what will happen to -13 into +11 if following the same method of unsigned multiplication? So if we follow the same procedure of unsigned multiplications here in the signed multiplication, so what will happen? So here multiplier, here multiplicand, the given multiplicand is -13. So what we have to do here, we have to take the positive of 13, convert that into a 2's complement value. So that is nothing but 10011. Okay, so then the multiplier is nothing but 01011. So we need 5-bit value to represent these two numbers. So then same, the method of unsigned multiplication will follow. If the bit value is 1, you need to write the same multiplicand value here. Then here we use a sign extension concept. So we need the product, the final product should be 2n bits. So here the bit value of the number of bits used in multiplicand and multiplier is 5 bit. So the product will be 2n bits. So 2 into 5, 10 bits. So here multiplicand we have only 5 bits. So another 5 bits we need to make it a 10 bits partial product. So what we will use here, sign extension concept we'll use. So here the MSB bit value is 1 here. So we will extend this sign bit value for another 5 bit value. Okay, so 5 positions here. So totally 10 values. The 10 values will come as a partial product. So next again we have in the multiplier we have 1. So 1 into m, same multiplicand value, here it is 1. So we'll extend with the MSB value. So another 4 value. Next is 0. So the partial product value will be 0. So here for each partial product we need to leave one space here. Okay. So then next is 1. So multiplicand value. Next the last value is 0. So we will write all values as 0. So now we will add this. When we add this, so we will get this value. So this is nothing but a minus 143. So the value what we got here is nothing but minus 143. So here the bit value whatever we given in the red color, that is nothing but the sign extension concept used. Okay, so this is the method of unsigned multiplication which we used in the sign multiplication method. So now we'll see the example for Booth's algorithm. So in example 1, we'll consider positive multiplicand and positive multiplier. So we'll take multiplicand as plus 13 and multiplier as plus 6. So what we have to do first, we need to recode the multiplier. So here multiplier is nothing but 0, 0, 1, 1, 0. So we need to add 1 0 here. Okay, we implied a 0 here. Now we'll refer the Booth's recoding table given here below. We'll refer this table and we'll find out the recoded multiplier. So 0 to 0 is nothing but 0 into m. 0 value, then 0 to 1 is 0 to 1. 0 to 1 is minus 1. Then 1 to 1 is 0. Then 1 to 0 is plus 1. Then 0 to 0 is 0. So this is nothing but our recoded multiplier. So 0 plus 1, 0 minus 1, 0. So now we'll apply the multiplication, sign multiplication procedure here. So here by using a sign extension method. We use sign extension method here. Here MSB bit is 0. So we will extend another 5 bit with the same value. So 5 zeros we will add. Then next is minus 1. So minus 1 means minus 1 into m. So minus 1 into m means we need to take 2's complement of the multiplicand. So we'll take the 2's complement. 2's complement of multiplicand is nothing but 1, 0, 0, 1, 1. So here MSB value is 1. So we'll extend the remaining 4 bit with the values 1s. Then the next recoded multiplier bit is 0. So we will write all values as zeros. Then next one is plus 1. Plus 1 means plus 1 into m, multiplicand value. Remaining 2 positions will fill it with zeros. Then last value is 0. We'll write with the zeros. Then do the addition. We will get this value. So here we will get one extra carry out, so that we need to ignore. So the remaining bit, the 10 bit value what we got here, that we will consider as a product of the product from this multiplication operation. So this is the product, that is plus 78. So here MSB value is 0. So MSB value is 0 means it is a positive number. So plus 78. So if you take the 2's complement this, so this is a example 1. So next we'll go to the second example. Here we'll take positive multiplicand and negative multiplier. So plus 13 and minus 6. So minus 6 we need to convert that into, first we need to consider plus 6, then take the 2's complement of the plus 6. So we will get the value as 11010. Then add 0 here, extra 0 should be added. Then we take the recoded multiplier. We'll compare 0 to 0 means 0, 0 to 1 minus 1, 1 to 0 plus 1, 0 to 1 minus 1, 1 to 1 0. That becomes the recoded multiplier. Then we'll apply multiplication procedure. So 0 to multiplicand m is nothing but 0. So we need to use a sign extension concept. So here MSB bit is 0. So we'll fill another remaining bits with the 0 value. Then next minus 1. Minus 1 means you have to take 2's complement of the multiplicand. So 2's complement of the multiplicand we need to take. So that is nothing but 1 0 0 1 1. Multiplicand is nothing but plus 13. We need to take this plus 13, convert that into 2's complement. Then plus 1. Plus 1 means same multiplicand value you need to write, that is 0 1 1 0 1. Here MSB value is 0, so remaining values we need to write it with 0 value. Then minus 1 means again 2's complement of the multiplicand, that is plus 13 we need to find out. Then last one is 0. Then replace with fill this value with zeros, partial product. Then finally find out the product. So this is the product what we got, that is minus 78. So to verify whether it is the answer is correct or not, just take another 2's complement of this product value, you should get plus 78. So that means this is a correct answer, that too minus 78. Next, example 3, we will consider negative multiplicand and negative multiplier. So both the values in negative form, so we need to take 2's complement of this. So 2's complement, we have taken plus 13, we have taken the 2's complement of plus 13 and 2's complement of plus 6. So here the multiplier is nothing but 1 1 0 1 0. So we need to add 1 0 here and we need to find out the recoded multiplier. So the recoded multiplier is nothing but 0 minus 1 plus 1 minus 1 0. So that becomes recoded multiplier. So now we'll apply the multiplication procedure. So 0 to multiplicand, so all the values 0. Next is minus 1 of the multiplicand. So already we have taken a 2's complement of plus 13, right? Again we have to do the 2's complement of this multiplicand. So when you perform 2 times, then you will get the plus 13. So that is nothing but 0 1 1 0 1. Okay, 2's complement of this is nothing but plus 13, 0 1 1 0 1. So here MSB bit is 0, so extend the sign bit. Next is plus 1, the same multiplicand value we need to take, that is 1 0 0 1 1. Extend the sign bit. Then next value is minus 1. Take 2's complement of the multiplicand, you will get plus 13. Then the last value is 0. So when you add this, you will get this as your product. So you will get one extra carry that we need to ignore. So the answer is nothing but plus 78. So minus 13 into minus 6, you should get plus 78. Next we will see example 4, negative multiplicand and positive multiplier, plus minus 13 and plus 6. So here minus 13 we need to take 2's complement of plus 13. So we have got 1 0 0 1 1. Then we need to take the plus 6 here, which is a multiplier, add 0 and find out recoded multiplier. Then find out the product. So here the product what we got here is minus 78. Minus 13 into plus 6 minus 78. So when you take 2's complement of this product value, you will get plus 78. So Booth's algorithm, which is one of the well-known sign multiplication method. So we'll see best case multiplier and worst case multiplier here. So best case multiplier is nothing but the multiplier which is having a long string of ones. So that we can consider as a best case multiplier, and worst case multiplier will be having zeros and ones, means alternating zeros and ones. So if you see here in the worst case multiplier, when we have alternative zeros and ones, so it will be very difficult, means every bit value we need to change the multiplicand value. So one time it will be -1, we need to take the 2's complement, then we need to take the multiplicand itself, again we need to convert that into 2's complement. So it is a worst case multiplier, it is considered as a worst case multiplier. And good multiplier means where you can see a long number of ones, then we can see long number of zeros, then again long number of, means a long string of ones and zeros. So it will be this kind of multiplier, it will be very easy to handle by using Booth's algorithm. The Booth algorithm has two attractive features. First, it handles both positive and negative multipliers uniformly. So we can handle both positive and negative operands here. Second important feature is that it achieves some efficiency in the number of additions required when the multiplier has a few large blocks of ones. The speed gained by skipping over ones depend on the data. On average, the speed of doing multiplication with the Booth's algorithm is the same as with the normal algorithm. So mainly the Booth's algorithm is used to speed up the multiplication process. So that is what Booth's algorithm. The main advantage here is that we can use this Booth's algorithm for both positive and negative number. That means we can use this algorithm for signed numbers multiplication. Thank you.